Now we move to artificial neural networks as opposed to looking at neurons. So we are going to start hooking up neurons in multiple layers like this, and the way we are going to train this is using gradient descent, right. Where we are going to train this neural network is using gradient descent. But what is the problem with using gradient descent for perceptrons? The non-linearity, right. So we had a threshold function which was not differentiable. For adenine we got around it by getting rid of the threshold function altogether. As I said, we will use a linear output, right. So what is the problem in using linear outputs in multi-layered perceptrons, right. So if you think about it, let us call the first layer weights alphas and the second layer weights I will call them beta, right. So if you think about it, so what you are producing is some alpha transpose x is the output here. If I did not have any non-linearity, if I just use a linear neuron, the output from here will be alpha transpose x, right. So z will be alpha transpose x, and what will go in here? Z. So y will be that which is equal to so just like having one layer of weights given by alpha beta. Right, there is no point in doing all this layering. So if I only have linear neurons, then I do not get the power of doing all the layering. I might as well have done a single layer of neurons. So I really need to do something non-linear in the middle. I need to have the threshold function for me to get the power of layering, right. So the threshold is actually needed, but whatever we did there, if I had kept it as linear neurons, we would have run into trouble, right. Great. So we need the threshold. So how do we get around the fact that so I am going to say that okay. And you get the drill. So y is y1 to yk, yeah. So where the sigma is a so sigma is like a soft threshold, right. So I can throw in a slope parameter here which I have not done, that will give me different rates at which the sigma will assign. So, the actual threshold will be that way, right. The sigmoid will give me a soft way of doing the threshold. The nice thing about the sigmoid is it is differentiable. Right. There are many choices that you can have for the nonlinearity, a differentiable threshold function. So, the sigmoid is one of them. So, the thing with the sigmoid is that it will be between 0 and 1. So, if you want it to be between -1 and +1, multiply by something, is it? That will go from -1 to +1, right. So, you could have different choices. So, for the time being I will stick with the regular the sigmoid that we are familiar with, okay. So, each z here will be given by that expression. So, T is the quantity that you will see that goes as the input to the sigmoid in the output neuron. Z is the output from here, from the middle layer, yeah, hidden layer. This one, that one or this one? 0 m alpha naught m plus alpha m transpose x. Can you zoom into that a little bit? கொஞ்சம் zoom பண்ணிக்கோங்க. Right, can you see it better now? People at the back who didn't complain the fonts are small, can you see it better now? So, what are I doing on the laptop? Are you actually seeing the video feed of this or something? No? Okay. Right, so that's the output of the first layer, okay, and the output of the second layer is given by some other function g acting on this input t, okay. Right. So, I would like to see if anyone notices something funny.
The middle layer should also have same dimension of the initial one.
Okay. Actually, all can be different. Okay.
Are those blobs that you have drawn, are those the nodes in there that correspond to a layer? Or
each one of these is a unit like this or that, like that, right. Each one of those is the one blob is a wala.
So, aren't there 3 layers over there in that case?
There are, good point. Okay, yes, there are 3 layers, and this is sometimes called the standard 3 layer architecture, okay, but the first layer is really a fake layer, okay. This layer is really a fake layer, it just takes x1 and gives x1 out on all the outputs, okay. This one takes x2 in and gives x2 out on all the outputs, okay. This is really not a neuron, okay. So, sometimes I like to call this as a 2 layer network, because for me there are 2 layers of weights, okay. So, it is a 2 layer network, right, but in the literature for some reason this is called a 3 layer architecture. So, this is called the input layer, this is called the output layer. Okay, one in the middle is called the hidden layer. So why is it called the hidden layer? Because I do not see the outputs of that layer directly. Okay, so they are called the hidden layer. So this is called the standard 3 layer architecture, but there are other ways of doing it where actually you take outputs from the middle layer as well, right, and you can do, and you can have inputs feeding into somewhere in the middle, so you can have all kinds of craziness. Okay, so the standard architecture is easy and we will stop with that. Okay, I am not going to go into all the crazy neural network architectures that are out there. So you might want to take another course on ANNs specifically if you want to know more about the all the crazy architectures out there. If there is time permitting, I will come back and do something very quickly at the end of the course, not today, but this is the standard architecture they will stick with. Okay, right. So still people haven't told me if there is something odd about this. Yeah.
So the last layer always has to be linear.
Last layer always has to be linear, not necessarily, but it did not also be sigmoid, that is why I written it as GK. So the last layer could be sigmoid, it could be linear, right. When would you want the last layer to be linear? When you want it to be linear is when you want to do regression for sure, right. When you want it to be a sigmoid is when you want to do classification, right. And still people haven't told me what is odd about this. I am assuming people are all thinking about it. I am waiting for the answer so that I can go on, that is why I am stalling. Yeah, so why did I write this directly as alpha m plus alpha m transpose x, alpha not m plus alpha m transpose x, but here I split it up into tk and fk.
GK or different GKs.
Sorry?
It's a consistent sigma. The sigma is the same which applies on here you are applying it.
Good point. But why is it t? Why is it not tk? So if I am doing regression, I might as well do it tk, right. So usually because my regression variables, right, if I am doing multiple output regression, okay, I am not talking about multiple input regression, multiple output regression, my output variables are typically taken to be independent, right. So I mean, so what value I predict for one usually does not affect the prediction I make for the other, right. So I don't know if you read the book. I didn't talk about multiple output regression before this, but if you read the book, they would have actually told you that you can do the regression independently, right. But if it is classification, okay, really it is not independent. If I am going to be outputting class probabilities, right, they can't be independent, right. If I am outputting class 1 probability is high, then class 2 probability necessarily has to be low, correct. So I had to do some way of normalizing the outputs to produce probabilities, right. That is why I am saying that this will operate on the entire T, okay, and produce a output probability vector. So in case of classification, you need it to operate on the entire T. So we will come back to that in a second, right. For classification, we will do a softmax like we did for logistic regression. So remember that. So e power yeah. So I need the summation over all the outputs, right. I need the summation over all the classes in the denominator, and that is why my GK operates on T. Okay. So this will be the softmax thing. So e power Tk divided by summation e power Ti. Right, this will be the Gk of T. Right. So what will happen if it is a single class, I mean it is a 2 class problem?
1 minus of
It will reduce to a sigmoid. It reduces to a sigmoid. I can pick one class and have that output as a sigmoid, and I can just say that okay, if this is greater than 0.5 then it is that class, if it is lesser than 0.5 it is the other class, correct. So if this is a 2 class problem, the GK will reduce to a sigmoid. So if I am doing classification with only 2 classes, I can straight away keep a sigmoid as my output neuron, and then I can solve it. How many neurons I need? 1, right. Suppose I am solving a 3 class problem, how many neurons I need as output? 3. Well, you can always have the third one as dummy, and then you can say I am going to do 1 minus the sum of the rest, right. But if you are going to do this, right, so I can always say that okay, I am going to have 3 outputs which will give me the probability of each of those 3 classes, okay. That is typically how it is done. For 2 you just have 1, right, but then for more than 2 classes you typically tend to have as many at the output. Okay. Is there any problem for doing that, with doing that? Think about it, I am not going to give you the answer, right. Okay, so how do we fit the neural network parameters now? Right, I have 2 layers. The first layer and I m into p plus 1 parameters. So m for right, so m for each of the hidden neurons, right, p for the alpha m's and plus 1 for the alpha naughts, okay. And in the second layer okay, likewise. So I have that many parameters that I have to fit. So I have to find all the alphas and all the betas. So why don't I do more layers than this? Why did I stop with only 3 layers?
It must be harder and harder to train as you have limited.
Yes, so empirically people observe that it is harder and harder to train. Why does it become harder and harder to train? I will tell you in a minute, okay. But there is another reason for stopping with 2 layers, right. So if you think of these as some kind of Boolean gates, right, if you think of the neural networks as some kind of Boolean gates, it turns out that I can implement any Boolean function just using 2 layers of neurons, except that the branching will become very large, right, but I can still implement any. So as long as I do not give you any kind of gate width, right, I can have as many inputs coming into a neuron as I want, right, I can implement any Boolean function in just 2 layers of neurons. So why is that? All of you know that, right? You can write min-term expansions, right? So all of those things you know that, and so you can essentially implement it in 2 layers of neurons. And people thought, oh, 2 layers is sufficient, it's a universal function approximator, I can represent any function I want, so let me not even think about higher layers. So that is one school of thought, so people stop there, but then there are others who are interested in going into more complex neural networks, because they did observe that when they got it to work, right, adding more layers worked well, okay. So people kept at it and they made it work more robustly, and so like I was telling you, the third wave of neural networks is all about having deep networks where you have more than 2 layers, right. So regression, what will be your loss function? So I am going to say define my regression loss for the parameters theta. What are theta here? All the alphas and betas, okay. Just wanted a single notation for the parameters instead of saying alpha beta every time. So I will say theta is given by essentially the squared loss, right. That should look really familiar to you guys by now, because we have been writing squared loss almost once every class, if not oftener. So what about classification? What can we use for classification?
0.
Yeah, but 0 1 is an incredibly hard loss function to optimize, right? So you could use squared error itself, right? So what is the rationale for using squared error? Same rationale that we used in linear regression, right? So yik is an indicator variable, that is one that gives you the probability of this particular data point being class k, right, and you are trying to fit the probability anyway, that is what you are trying to fit, and therefore for every data point you can take its probability of being class k is 1 or 0, and then you can try to do some squared error and try to make a prediction, okay. That is one way of thinking about it. The other way is to use what is called the cross entropy error or the deviance, which is related to whatever we did in logistic regression. So here I will define my So we will output the actual class label as the one that has the highest fk of x, like we did in the discriminant based classifiers, except that fk of x is no longer a simple discriminant function, right. And so this is essentially a error term, okay, that stands in for likelihood that we maximized earlier. So and to optimize this error term, we will essentially train the neural network using maximum likelihood, right. So I am not going to go there. So we will look at a more popular mechanism for training neural networks, which essentially looking at the gradient, the squared error and do gradient descent, okay.